On behalf of Evoke 3D, HP and Ability Made, welcome to this webinar on digital workflow comparison for orthotics and prosthetics. My name is Joe Carmody, Managing Director of Evoke 3D, and I will be facilitating this event today. We have a great audience in attendance from across Australia and New Zealand, as well as many people joining from overseas. Welcome to each and every one of you. Thank you for choosing to spend this time with us here today. Before outlining the agenda and introducing our speakers, I'd like to quickly introduce Evoke 3D and our mission. Founded in 2013 in Melbourne, Australia, our mission is delivery of high quality additive manufacturing solutions, which includes supply of machines, materials, support and software. We're focused on delivering end-to-end solutions to meet the manufacturing needs of our clients, includes digital file preparation, 3D printing and post-processing. Our aim is to span from art to part, if you can put it that way. Over our 11-year journey in 3D printing, we've become involved in digital transformation of a number of industries, including dental, orthodontic, audiology, jewellery, eyewear, orthopedics and others. However, the application that is most exciting to us and the one that delivers truly life-changing patient outcomes is orthotics and prosthetics. Now, O&P is a hugely complex area of healthcare, and we don't presume to hold the depth of knowledge and experience of the many O&P practitioners that are on this call. But we do hope that this webinar will deliver some insights or at least provoke new questions around how direct digital manufacturing could be used in your practice to deliver improved patient outcomes together with better productivity. So rolling into the agenda and introduction now. So we have three presenters joining us today, and I will provide a more detailed introduction before each section, but here's a quick overview. So first of all, we've got Aileen Fernandez from HP, who will be presenting on making the transition and some of the many considerations that should be addressed in that process. Then we've got Simon Bartlett from Evoke 3D, who has conducted some time and motion studies to actually quantify the productivity gains from traditional versus direct digital manufacture for prosthetic sockets. And lastly, we've got Corey from Ability Made, who will outline their real-world experience in deploying a complete end-to-end digital workflow to deliver world-leading pediatric AFO products. At the end, we'll have a Q&A. So if you could please put your questions in the chat, and we'll endeavour to answer all of them at the end of the session, time permitting. So moving across to Aileen now. Now, first of all, a very special thanks to Aileen for getting up very early in the morning, and she's joining us from Barcelona. So thank you, Aileen. Aileen's worked for HP for over 7 years, with 5 years direct experience in additive manufacturing. She's managed various healthcare segments, including surgical guides, medical equipment, medical devices, and is now focused on O&P as the global segment manager. Aileen's goal is to support customers to improve their operations by adopting AM. She works hand in hand with a large team of application engineering, R&D, professional services, and CPO professionals to support customers not only in the printing process, but importantly across the digital journey. So thank you, Aileen. Over to you.
Thank you. Thank you very much. So yes, as Joe says, very early here. So whatever is wrong, I'm gonna say that is the sleep deprivation. So if we move forward, Simon, to the next slide, I want to talk super quick about the opportunity. So probably you saw those numbers, so you have similar numbers as well. We are talking about the 7 billion opportunity with a growth that is very consistent over year. And why is this going on? Essentially because the aging population, diabetes, and all the illness that are going on in the in the world. Also, the increasing product offering that we are seeing in the O&P space is not just limited to a couple of them. Now, the roadmap of potential devices that an amputee or a person can use is increasing significantly. Also, the geographical expansion, we are seeing a lot of companies trying to keep developing new devices overseas, and also the benefits of the new custom orthotic and prosthetic devices. And the interesting thing about this is in HP, we are working in different industries, but we are seeing that O&P specifically is the industry that is making the transition to digital in a more significant way. And why is that? I always like to say that it's because what O&P space needs is what additive manufacturing can provide, right? So when we are talking about O&P, we are talking about a need of personalization. We are talking about a need of part performance. So we need to have a minimum of performance in the different parts. And also we are talking about economics, how we can have affordable devices, but also very important, how we can scale our production in a more cost-effective way. And also something that was very, very evident during the COVID, it was, hey, how we can simplify the supply chain to have the products that our patient needs on time. So this connection between what the industry and what the field need and what MJF specifically, or the additive manufacturing industry, can provide is matching in a very significant way. So if we move forward here, Simon, you're going to see that probably the people that is in the call can resonate to all of them, to most of them, to some of them. But what I'm seeing talking with people in the industry is some of the current challenge that we have is still a very labor intensive when we think in the traditional manufacturing process for O&P devices, right? And what's the problem with the human labor intensive? The problem is you can have more errors, right? When you are doing more manual interactions, the amount of errors that you can have increase significantly. And this is still an industry with the people that they are working on manual workflows. The second one is related to the scalability and how expensive the scalability will be. I'm sure you have, there are some O&P manufacturers in the call, and you can relate to this. So when you want to expand to a different product, when you want to expand your production, this is not affordable when you are working with manual process. So we need to somehow, as a whole, solve this. The third one that I discussed this with a lot of clinicians and CPOs and people in the industry is related with the data that we are digitalizing versus the data that we are not digitalizing yet, right? And only patient data can be digitalized. And the problem here is a lot of data is lost when we are doing manual process. And the fourth one is related to the high volume of waste that you have when you are working on CNC, more traditional manufacturing process, right? And the volume of waste is first and foremost is related to sustainability, but also very important is related to the cost that has to storage all that waste. So labor intensive, scalability, data that cannot be digitalized, volume waste. Those are some of the issues that we see all the time when we are talking with people that they are manufacturing in traditional. So Simon, if we move forward here, you're going to see that this is related to probably the manual workflow that we have been commenting, right? And what are the processes? So, these more than us, but we are talking about, okay, we need to evaluate and diagnose and prescribe, then submit the order, ship, fit, and use. But if we move forward here, we're going to see that, okay, the process of do the plaster impression can be cheap, but also we need to wait until dry, and time is also money. The removal can be uncomfortable, depend of the patient. Also, we're going to see that there are multiple steps that, as we say, can have different errors. For children, this can be very, very challenging as well. Some muscle memory issues. Going backward is very hard. So when you have the final products, it's very hard to go backward. When we move forward here, we're going to see that this take around two weeks. This can vary a bit, but this is an average of how much is taken to manufacturing an O&P device. And when we move forward, we start thinking on what the current process needs, right? So when we are thinking on, okay, this is my manufacturing process today, what should I do to have a better and a more consistent workflow? So first, we need to have fewer steps to create a socket in this case, or any other O&P device. We need to reduce the lead time significantly to have a more affordable production, a better lead times. We need to have inexpensive materials. Still, we want to decrease costs and democratize solutions as much as we can. So this is an important point. A very accurate process. We need to make sure that what we are measuring and the data that we are obtaining is very, very accurate. Gentle method with the patients. I believe this is super, super important, not only, for everybody, for children as well, but for everybody, have a very gentle method. Adaptable method for children's, ability to identify and visualize the patient anatomy, and also the ability to make detailed changes when it's needed. So this is all that the manual workforce needs to evolve and to jump to the next level. So if we move forward here, you're going to see that the digital workflow in terms of steps is very similar, but there are, of course, all digital interaction instead of the manual interaction. So we are going to have a digital scanner taking the information from the patient. Then we are going to need to manipulate that data to convert it and then print it, of course. So probably some questions that are popping up there is, okay, but the scanner can be controlled, how accurate is going to be? Or other question that they have a lot is, okay, but I'm not familiar with CAD, I'm not have experience with software, so what can I do? Can I actually produce something that I envision? I don't have experience with 3D. And those are all the points that we are going to cover, not only in my part, but in the whole session, right? So how the scanner works, how the software works, and how the printing process, it's actually, spoiler alert, the easiest part of the process. So if we move forward here, just one more time, I want to make the comparison. So we described what the current process needs. And so what's the new process needs then? So a couple of things, and I want to mention always 5 that I think they're very significant for the industry. The process should create the product that we initially envisioned, right? So the idea that I have on my mind can be created along the process. Also, the process should be very easy to manage. And this is important. This is important because 2 main things. First is we are starting to digitize the industry, and it needs to be easy to be adopted faster. And also because as easy to manage is going to be easy to incorporate. So you're going to waste less time trying to incorporate new methods. And we want to have a very straightforward process out there. Also, written and practicum style learning methods that can be learned in your facilities. The software, very important, should be easy to learn as well. There are several software options. I'm going to mention a few of them afterwards, but this should be very, very easy to incorporate. Yeah, and if we move forward here, you have an example. There are many options in the market. When it comes to a scanner, I want to split them in 3, right? I want to talk about the basic ones that are more scalable and cost efficient. We can jump to the general one if we need probably a best output out of this. And we have also the dedicated one. Here you have some brands just as a reference, but it's important for you to start seeing that, hey, there are options for the different needs that you can have out there. And in the right part of the screen, you're going to see also different software options. You have in the top of the of the screen, the one that there are O&P specific. So you're going to have probably a specific template and a specific geometry that you're going to adapt to your patients. Also, you're going to see that some of them are specific for applications, for insoles, for sockets, and other ones are multi-purpose. And also when you go down, you're going to see software that are more general purpose. when I'm talking with with customers in the industry or with people in the industry, the first advice that we always give is start easy, right? So probably the first thing that you can do to start is incorporate a scanner, incorporate a digital scanner to start the transition. And then in terms of software, it's depend on what you are doing, and it's depend on what you want to achieve. Depend your application, depend if you're working with children or with adults, because probably you need more accurate methods if you're working with children. So it depends what do you need. The industry is now very well populated with different options. Moving forward here, you're gonna see why we need to, or why we are really seeing this transition to digital. And specifically, I want to mention two big buckets, right? The first one is because when you do the transition to digital, you can see that the product differentiation is out there. You're going to see that you can have improved functions, you can have less bulky devices, more breathable devices, better patient comfort, right? And also you can see that you can have design freedom, you can have less adjustment, lighter weights, sorry. So this is important because you want to differentiate your products from competitors. And when you have additive manufacturing incorporated in your industry, this is way easier to do. In the second big bucket is related to the workflow simplification. And as we have been looking, you can have a higher productivity in a more affordable way. You can have predictable time to parts, so you know exactly when your production is going to be ready. And also you can reduce the waste that you have in your process. So moving forward, cranial orthosis, an application that I'm personally, I'm working globally, so I'm seeing the transition fully to digital in this application in other regions. So a fantastic application to try with digital. Prosthetic fairings, coverings, prosthetic sockets, of course, scoliosis braces, prosthetic arms. So different applications out there that a lot of customers are already producing with additive manufacturing. Moving forward one more time, some examples that I want to mention here. One is from Invent Medical. As I mentioned, this is a great application for additive manufacturing. It's a cranial remolding orthosis. It is a baby helmet, as we call it as well. And you're going to see that this application should be used for a baby for 23 hours, right? So what do we need from this application? We need an application that is very, very lightweight. We need an application that is very breathable, and we need an application that is very comfortable, right? So when you're scanning the baby and having exactly the baby anatomy, you can have something that is very, very accurate for the baby and very comfortable. Also, you are going to see that in this case, Invent Medical reduce significantly the weight of the part and make it very a lot of improvements in the device itself. Moving forward one more time, another application that is fantastic. I absolutely love this application because they are combining different materials. They are combining a very flexible material, which is a TPU in this case, with a rigid material to work with the stiffness that you need for a prosthetic socket. So also they design some kind of paddles internally to add extra comfort, and they have an adjustment to make it easier to put it on and put it off in a more comfortable way. So those are the kind of things that is very, very hard to do when you're working with manual, but you can do more cutting edge devices that are really improving patient life. All right, so if we move forward here, I think we're almost done, and I'm gonna move to the other ones. But our mission is everything that can go digital will go digital, and that's what we are working on. Moving forward, this is the MJF portfolio. We can deep dive on this in any other session. Quite data file, the file preparation, and also how is the printing process itself. And at the end, I'm seeing some questions popping up about materials. If we move forward, a quick snapshot on which are the materials that we have in HP. There we go. So we have different rigid materials, different flexible materials. Almost All of them are biocompatible, so this is a fantastic asset if you are looking for material that is suitable for O&P devices. So I tried to go a bit fast and furious because I know we have more content. I'm gonna stay at the end of the session, and we can cover any question you may have. Thank you very much.
About the socket so far?
I am thinking that it is the lightest that I've had in 16 years. Extremely comfortable. It was, stepped right into it. It was a perfect fit from the get-go. The weight, I can't explain. The weight is, you get to really small amounts in pounds, you start breaking it down. The weight is second to none, literally, good expression, second to none. I can skip, I just skipped. I haven't skipped in a long time. So, I'll show skip. I can jump.
Thank you, Aileen. That was great. And I think being in Australia, it's important that we look to the rest of the world, North America and Europe, to see the trends and the innovations that are taking place. And Aileen brings that to the table in terms of the global head office in Barcelona for O&P. So thank you, Aileen, for getting up very early and sharing your knowledge with us. So next up is Simon Bartlett. So Simon has over 25 years of engineering and management experience working in demanding roles across 3 continents with some of the world's largest multinational companies. Since completing his studies at Swinburne University, Melbourne boy, he has worked in both design, development and management engineering roles. Simon helps organisations transform the way they work using lean manufacturing methodologies to drive process efficiency improvements, build high-performance teams, and adopt the latest in advanced manufacturing technologies. The result, increasing shareholder value by setting a clear vision and delivering on that vision. So over to you, Simon.
So thanks for the introduction, and I got to also say a big thank you to Aileen too. Understanding it's 4:30 in the morning, so to be that articulate in a second language is fantastic. So thank you. What I'd like to try and where I'd like to sort of kick off today too is 2 slightly different sort of themes. And the first one is, I'm not sure if anyone on the call is familiar with the business leadership expert Simon Sinek. Simon produced a book back in 2009, which actually had a big effect on my professional and personal development. Now, the book being called Start With Why. And I wanted to start with this because, as you can see with the guest speakers that we have listed, we've got a fairly heavy engineering sort of focus, whereas a lot of people on the call maybe come from that clinical background. What I'd like to sort of stress is, despite our differences, we actually all start with a common why. And so Evoke and our common why is effectively better patient outcomes. As we start with why, the second concept that I wanted to sort of bring up today as well was what we call the Medici effect. Now, the Medici family, for those of you, we're going to have a little bit of a historical lesson here. Medici family actually ruled Florence from around the 1500s for about 300 years. So not only producing leaders, they also produced a couple of popes in their time as well. But they were patrons of the arts and the sciences. And what is important with that is they felt bringing different people together from different backgrounds and different educations, etc. This was actually a catalyst for driving innovation. And they are actually given the title that they were actually able to help and drive the Renaissance period sort of that we saw through Italy for that time. The catalyst, so we have our common why. But then also if you think about this Medici effect, we've got engineers and clinicians coming together, and what we really need to do is sort of show that collaboration. And I think that's what we help to show by not only the speakers that we have today, but I think our last speaker today, Corey from Ability Made, I think it'll really help to sort of show the benefits of that outcome. And as I said, it all starts with that common why. But just diving a little bit into 3D print and the wheelhouse that is 3D printing and why I guess it's so relevant to the topic that we're talking about today. if you can imagine, the more of these ideas that you have sort of shown up here, these 5 ideas, the more that you can incorporate these into your design, the better suited it is towards 3D print and maybe away from traditional manufacturing processes. You think about, you know, part complexity. I mean, you can see that socket there, you know, part consolidation, where we're bringing multiple different parts and assemblies together and printing them all as one piece. We have you can actually bring together vertical integration and by printing on demand. So we don't actually have a lot of stock sitting on a shelf. Enabling functionality, again, as you see there with the socket that we have went from one particular part, we have multiple different design aspects. And then, of course, particularly to this application, we have personalization, because, of course, all of our biometric data is completely different. And I guess the other value adds, which is sometimes a little bit harder to quantify, is, and ALN touched on this earlier today, you know, like earlier in the presentation. So what we saw with COVID, that we had a complication with supply chain by bringing things in-house and closer to the point of personal care can simplify that supply chain. Digital warehousing, you know, we're now keeping digital files and we're keeping powders, etc., as opposed to keeping, you know, stacks and volumes of raw materials. Part consolidation was mentioned in the previous slide in terms of being able to bring that, incorporate that into a design. But the other side to part consolidation too is it helps with reducing human touch points and improving production, not only in terms of time, but productivity, but also in terms of part quality as well. Reduced time to market. Again, there is time compression that has there, and tooling costs. Tooling costs maybe not quite so relevant for this application, but for other applications where instead of having a capital tied up in tooling, but then also in spares in warehousing, 3D printing helps us to get over that. Okay, so that's our why. So as I said, we start with a common why. Now, if we start to then drill down and going through this golden circle, so now we start to look at the process itself. And again, ALN already sort of touched on this, and again, Corey will go into this a little deeper. I guess what we're trying to show now is, as we go from that 40,000 foot approach and come deeper, one of the things that we do at Evoke is do this time in motion study, because that helps transition. It helps for people to understand maybe where their waste is and where they can get process improvement and help to bring down costs. If we look at our traditional manufacturing process, you know, we start with, you know, either with a scan or with a cast, etc. And I won't go through this in fine detail. Obviously, time as we go through those processes and to those sort of steps, and I'll do a summary at the end. And then if we look at that transition to a digital workflow, and again, you know, we start either starting with a scan, etc. But one of the things which is unique going to a digital process is that repeatability of process. And some of the software which we've been using and some of our customers are using too is Entopology. So Entopology is ideally suited for digitizing workflows. So all of those repeatable processes. So we can actually get that design process down now to sub 10 minutes for a customized device. So that's basically going from uploading scanned data to an output printable file in under effectively sort of 10 minutes. And it's a repeatable process. Again, not only does that help for the time compression, but there's a quality improvement that we see too, in that we have a repeatable process and repeatable steps. But if we line these two processes up side by side, you can see here under the time column, we've got the human interaction time, and then we've also got the time, whether it be for, you know, drying, etc., or the printing process, which is I guess the dead time, which we have no control over. And these numbers were actually qualified by one of our recent machine purchases out of Masson's. Okay, so these numbers do come from the field, and I did not just pull them out of my polished bald head. Okay, so we've seen that the hands-on time to make a socket, we're looking at about just over 4 hours, just under 4.5 hours. And that's effectively over a 2-day process, so a 2-day period, if we look at the machining time, the curing time, etc. So this is the quickest that we could possibly get a product out the door. Now, if we flip over to a digital process, We are still looking at a 2-day turnaround time, but what is unique with when we're printing is we can actually manufacture more than one socket at a time. Okay, so if we look at the summary at the bottom there, we can print 6 sockets at a time. So as long as we've got our design workflow condensed to a point, that shows a massive increase and ability to scale. Some of the other things which we need to really look at too is a lot of the resins we know of are known carcinogens, but the big one too is the amount of waste. On estimate, we're looking at about 45 litres of waste per socket. And so that is not only the what's left from the machining process, but it's also the excess in resin, it's the containers, it's the gloves, it's the bags, it's all of the items consumed in that process. Now, on the flip side, if we look at the printing process, if we talk about printing 6 sockets at a time, that equates to around about a packing density of 8%. Okay, so when I say a packing density, that's the number of parts that we can physically fit into a build chamber. Okay, now working on that type of packing density, we see a waste of around 410 grams per part. Okay, and that's actually in used powder, which is consumed in the process. If you'd start to compare those, 2 items, we've not only got a time compression, but we've also got really big improvements in terms of our green footprint as well. So moving on to our what. So this is now going further out in this golden circle, and now looking at what is our product and what is our output. Now, what you'll see here is the evolution of a socket. And so this is the latest product, which is from Invent Medical, which is locally distributed by the team out at Massons. If we think about, and as we'll go through and show in the next couple of slides, and if we think about what was shown previously, in terms of that wheelhouse, which is 3D print. So what we see here is we've got part complexity, we've got personalization, we're built to order, and we've got added functionality. So we are ticking a lot of different boxes in this one product. What we need to do, and this is something which the TGA is not asking for yet, but it's something which will definitely sort of be coming down the pipeline, is how does the product function? What is the testing rigor that you've shown that your product is fit for purpose? Invent Medical have gone out and they've actually already done this. Right now, ISO 10328 appliances, it's around the products which actually bolt on to the socket. The socket itself does not have any testing requirements as to date. But testing to those same parameters, though, as we assume that all the other items which bolt onto it too, Invent Medical are not only printed in a number of different materials, we've got a PA11 and a TPU, but it's surpassed 1.5 million cycles. So it's gone beyond testing requirements for all of the componentry that adds onto it. And with that, there was no signs of fatigue behaviour, there was no cracks, there was actually no change in shape. So any deformation was elastic and not plastic. So that's a positive in terms of dynamic testing. Now, if we take the next step using basically taking the part to its breaking point. First 2 tests which we're showing there is of a standard socket. So this is testing, doing a complete back-to-back test between a printed socket, in this case it was PA12, and an exact replica of that socket done in a traditional way, which is carbon fibre. So you'll see there in terms of ultimate strength, one is the PA12 socket actually broke at a high point. But what I think is actually a critical point to this as well is if you look at the static displacement. Whereas the socket was able to survive longer, the printed socket, it had the ability to flex more. So it wasn't as stiff. I'll go into that a little bit further in the next slide. Comparing what we've done there in terms of a back-to-back test and look at what we've done or what Invent Medical have done. So they've taken that Orgo socket and they have gone and tested it again to the same test. They stopped at 5,000 newtons, and that is effectively the maximum testing strength of the testing apparatus. It didn't break. The closest thing that broke was actually the testing apparatus itself. But we didn't see any failures. There was no plastic deformation, so no permanent deformation. And so afterwards, the socket was still fit for purpose. What we're trying to show here is as we take that next step, what we need to show is data. And this is what engineers can bring clinicians as we come together, show us the designs, and let's work out how to test and improve and make that a cyclic process. just going back to what I mentioned before in regards to stiffness, and I guess this is the evolution maybe of a socket too. If you hark back, 20, 30, 40 years ago, cars were built stiff. They were built out of steel. They weren't actually designed to crumple, and you can see a couple of pictures there. So, these are quite severe accidents where all of the forces and all of the loads, as you can see, first law of thermodynamics, okay, energy is not created or destroyed. Okay, so all of the loads that we're seeing there during a crash test are actually going through to the occupant. Now, if we fast forward that evolution, we can actually design things to crumple. We can design to move and how to distribute energy. And I think this is what we're really sort of now seeing too, is as we go from something like carbon fibre, which is stiff and rigid, we have actually the engineering tools now to tune materials through a printing process to make them a better fit. So we're not just transferring all of that load directly through to the patient, but we can distribute those loads more evenly and cushion any of those loads as they're distributed to the body. And I think that is one of the biggest performance improvements that we're seeing. And so just quickly to summarise before I hand over to Corey, I guess a number of the key takeaways I think from today. So one is, look, the time compression that we saw. So in terms of the labour intensity, we've got a compression or an improvement of 65%. With that, we've also got an increase in throughput. So remember, with that spare time maybe that we have now, we can also go into designing more products for more patients. It's a greener solution. So what we saw there was in terms of the weight of powder, which is wasted byproduct, versus what is going into landfill, which is also going to landfill from the traditional process. There's a massive change there. Reduction in cost per part. This is potentially relative. Depends on the case by case basis. Manufacturing flexibility. One of the slides which you remember that ALN showed is when we talk about, we aren't just talking about sockets here. We could be talking about insoles. There's lots of cranial helmets. There's lots of different products which printing then opens us up to, and all of them can be printed at the same time. So we have a flexible manufacturing solution. And with all of this too, what comes for free with 3D printing is we can increase design complexity, because complexity comes for free. And with that too, and something which Corey will touch on, is not only just in terms of functionality, but looking at improved quality in QC. It's a lot easier when we have a standardized process to go back and not only improve, but to check, if and when potentially failure can occur. So on that note, I'm going to pass over to Corey. I hope there was something in there for all of us, engineers and clinicians.
Thanks, Simon. And I think what comes across there is to make good decisions about your design or the economics of a particular application, you need good data. So that's what Simon brings to bear. And for all of you on the call, if off the back of this webinar you've got a specific application or a use case that you'd like to explore for direct digital manufacturing, please contact us, and Simon can work with you to really get into the detail on that, and see whether it is the right application or not, and what would be involved. So thank you, Simon. So next up we've got Corey. Corey Killick is from Ability Made, and he joined Ability Made in 2018, fresh out of university, after completing his honours thesis on mechanical testing of 3D printed orthoses in 2017. So you can see again here, and we've got some questions already around safety and strength and durability, but you can see how this is very relevant in your industry now. So Corey was awarded the Engineers Without Borders Excellence Award for that work. Congratulations, Corey. Corey's current role is Head of Product, and he is responsible for product development and production at Ability Made. He's managed multiple types of orthoses right through the product life cycle. Corey also does product development and production at Ability Made, and he gets involved with the modeling as well. So he's intimately involved with the day-to-day digital workflow, works closely with Ability Made's in-house CPOs. So over to you, Corey.
Awesome. Thanks, Joe. Thanks for introducing me. Hi everyone. Yeah, I'm Corey. I'm a mechanical engineer by trade. Joe's already introduced me, so I'll jump right into it. So I want to explain how at Ability Made, how we use a digital workflow to design and manufacture orthoses, look into the inputs and outputs of the various stages of the process. So let's move on to the next slide here, Joe. Okay, so very quickly, who is Ability Made? We're a social enterprise. We work as a multidisciplinary team, and we're designing and manufacturing all the morphoses. We don't have any printers in-house, and essentially we outsource all our printing, and that's where I'll go into more about how we actually do that and how we actually do the testing to actually validate the print bureaus. We work with Orthotics as a central fabricator. We do hold some clinics. We do have in-house Orthotics. And yeah, we're not just a bunch of engineers thinking we're going to save the world. We do collaborate quite a bit with Orthotics, and they keep us definitely on the right track. Let's jump into it. Now, next slide here, Simon. Thank you. Cool. So I just want to, we've touched on this a few times in Alien and also Simon's presentation, so I don't want to go into it too much, but essentially I want to provide a bit of context for where we come in the clinician's workflow. So shape acquisition, there's a lot of amazing apps out there, amazing devices out there that have come out over the last few years where you can do really great shape acquisition, and that can happen a number of ways. And essentially from there, of course, the clinician, whether they're doing plaster mods and then scanning, or whether they're doing their mods in CanFit or Amiga or some other software. From there, essentially what we focus on is the external solid device shape. So taking the external solid device shape, manufacturing that, designing that, and then moving that over to a 3D printable format and controlling the whole process of getting it 3D printed and delivered to the orthotist. So I'll jump into what our digital design workflow. So essentially, we get the scan at the order submission stage. We get a prescription from the orthotist, and this prescription includes the client's weight, the activity level. We get a device prescription, so measurements, the rigidity that you require at various parts of the device, the kind of strapping that you will need, the padding, and we also have this. We've got one of our orthotist that calls it the magic box, which is the comments box, which is essentially just do a mind dump of what you would like to achieve. And essentially that's the information that we can utilize with the prescription, with the scan, and we talk about it with the whole team, with the orthotist to create a custom solution that you have essentially ordered from us. So from there, we get your scan, and essentially the scan input to our systems, we've got a lot of different scanners that are used by the clinicians that order for us. So we do need to standardize what the inputs to our 3D modeling process are. So that's where the pre-processing comes in. It's not just the cleaning of scans, but it's the repairing and the non-clinical alignment. So when I say alignment, just kind of putting it into the orientation in 3D space. That our 3D modeling software can essentially intake. From there, we've got our bread and butter, which is the 3D modeling that we do. So the inputs into this are all the information that we got from the orthotist, what we have turned it into from the pre-processing stage, and essentially the testing that we do determines our thicknesses, the geometries that we need to achieve, and that's also where we have things like the tolerances that come into play, and how we control the change in thicknesses, because that is essentially a critical part of getting 3D print right, which is controlling how the thicknesses change, not just what the thicknesses are, but how quickly they change across the device. I have put quality control right after 3D modeling. But essentially we do have a quality management system that touches on every single part of the process, and essentially we do have a standalone point, and we do have a standalone process after the 3D modeling stage before we send it off to the orthotist for review, where we do a mesh thickness analysis, and we look at the geometry. We do comparisons to the design specifications that we've built from the testing that we have done. and also compare it to the thickness selection. And I'll show you what that kind of looks like in just a moment. From there, we send it to the orthotist so they can see it in 3D. They can annotate it, provide comments, provide any changes that they would like, and then we'd make those changes. Again, take it through quality control again if there's any changes that were made, and then off to print it goes. After, of course, a lot of our devices get color mapped, as you can see in the devices in the backgrounds. So I'll jump into what informs a lot of our modeling specifications and our design specifications, which is the mechanical testing that we do. So there's a lot of different types of mechanical testing that we have to do, and that someone in the industry would need to do to actually go about a digital workflow. So before we even start, of course, which material are we going to go with? There's a lot of testing that goes on in terms of characterizing a material. So its impact strength, its flexibility, its fatigue life, and that's at the material selection stage. We continue that. So we've got a standard test piece that summarizes the characteristics of a material with the least amount of testing that we could do, and then we expand on it. You could see it in the photo with the little foot plate right there. That's a fatigue part of it. Yep, perfect. Thanks, Simon. And essentially, that's a fatigue testing part. So we and I'll go into a bit more detail about the results of the testing that we've done. But it's essentially, we've had parts printed at close to 50 locations using a variety of print processes: HB, MJF, SLS, SAF. And we've been doing a lot of testing around it, and I'll show you the results of that testing in a moment. And we have found that the HB Multijet Fusion 580 printer with its color, the PA12, essentially, when you couple it with the vapor polishing, produces really amazing outcomes. But I have been told that HB is utilized. We've been hypothesizing that essentially the great properties that we see in the color printers is because of the titanium oxide that's added in throughout the process. And we can see that in HB's newest machines in the 5420W as well. So we do have limitations in terms of what we can print, such as the build volume with the printers that we use, and that is 32 centimeters. And how we've been able to get around that is sometimes we extend out the toe plate or the calf area with a TPU. So moving on to essentially what do we test and the specifics of it. So the impact strength, when we think of the impact strength, it's really the amount of localized force that the material can undergo without cracking. So 3D printed polymers, it's all about preventing the crack from forming in the first place. So if you can prevent it from forming, then you're going to prevent it from actually propagating and running through the material and eventually cracking. So we did find that, you can see with Nolan 12 MJF, there's quite a big range, and at the highest range, we've got the Multijet Fusion 580 printers, and essentially from that we can see that those prints perform quite well at heel strike when you're running and jumping. If a client was to fall, the device does quite well in those modes. So the vapor polishing definitely helps, and that's where we could actually see the range for those for the same material. So nylon 12, we've got a range from 100 joules per meter to almost 250, and that range does come from the different print bureaus, the different print processes, and the vapor polishing, whether it's been vapor polished or not, and also the refresh rates. Because I saw a question earlier, definitely something that we speak about with the print bureaus when we're actually validating them, what kind of refresh rates that they're using, how long they're letting it sit, indicate before they actually take it out. So with fatigue life, again, vapor polishing helps quite a bit. And again, we did find a huge variance between different materials, print process, and the print bureaus. So we're constantly testing, trying to find out more about the process and looking for better outcomes. And I'll talk about a bit what those look like in a moment. But essentially, how does this relate to what we do? We provide a 12-month warranty on all our devices, but with the testing, we want to extend that out even further, and we've been able to extend it out. I think 2018 we were offering 3-month warranties. We moved it up to 6 months, and we're at 12 months, and hopefully we can keep increasing that as the material and the industry matures. Over to the next slide, Simon. So bring it all together. So it is a circular process. Our quality standards and digital testing feeds into our physical testing, where it's compared against and validated. That then feeds into our data-driven design. We've got thicknesses and thickness transitions and geometries that we actually need to adhere to, and we keep checking that. So the little SMO at the bottom right corner, that's essentially where the analysis that we do a mesh thickness analysis, and we can see what thicknesses the material is at once it's been designed throughout the material, and how it actually transitions as well. So it's not just about the thickness of it. Essentially, that little yellow zone underneath the red, where the dorsum is, essentially, if that's not wide enough, then that results in fractures, because the thickness transition needs to occur over longer distances. So the design requests that we get also feed into what we test and how we test it. So I want to share a few learnings that we've had, and I'll be lying if I said 3D print works for every client and device, of course. So if you need a super stiff, thin device, 3D print is not going to cut it. We tried going down the pathway of incorporating triple action joints and Euro springs into our devices, but to get the same thickness, it's the same stiffness of a comparable carbon fiber laminated device. I'm not even talking about pre-brake, not even trying to go there. We ended up with a really thick, really bulky, heavy device, and it just didn't have enough torsion rigidity, even when we got up to really thick, really high thicknesses. So where do we go from there? So over to the next slide, Simon. So instead of using a digital, so here's a good example. So we incorporated the TPU and the nylons with the laminates. So we let the carbon do its job and support the client, and let the TPU and the nylon do what it's good at, which is, so TPU is really amazing material. We've got a lot of great feedback around it. And essentially it's great with containment of soft tissue, and you can get the firmness that you need with lattices and the change in thicknesses. So TPU is a really amazing material where if you just add a little, it really goes from being a 2D material to a 3D material. So going from 1.5 millimeters to 2.5 millimeters, it really changes in properties because of how it's built, and can get rigid really quickly. So it's still stiff enough and can be made stiff enough to hold tissue, but still has some flexibility in it as well, even in the stiffer parts. So it's also a very forgiving material. I can see that Joe's jumping on because we're probably running out of time, so I'll speed through this last bit. So it's easy to adjust, to heat out and to grind. And also an added benefit that we also solve that is that if you need to, it's great with growth and changes in fit, so you don't need to replace the whole entire carbon shell and joint. Instead, you can just replace the TPU or the nylon part. So things like flexible toe plates. So we've got a PDE there. It's a little bit hard to see in that photo, but essentially that PDE was really great with having a dynamic stance space to rock over and mid stance. We got really good circumferential control in that. And that last photo just in the corner, that's just a solid ankle AFO with TPU. And again, we've got more circumferential correction and more coverage to hold the foot in place, and the TPU was flexible, and we really cut down the nylon, so it was great for dystonic movement. And yeah, there's lots that we could keep talking about, but I want to open it up to questions, and I think that's also why Joe's moving me along.
Thanks, Corey. No, I wasn't moving you along. We could talk about this stuff for hours, and
yes,
we'd love to. We'd love to, and hopefully off the back of this webinar, a few of you will contact us, and we can continue the discussion. But yeah, congratulations, Corey and Ability Made, for the work you do. We think it's amazing. It's world beating. So well done. And look, I think probably just we'll jump into Q&A now. We've got 3 minutes. So if the presenters want to just get their mic on and we'll share some questions around. I thought probably the first one, Corey, as a sort of follow on from your couple of things you mentioned, was around the minimum thickness that you can print before you have issues. So you mentioned the SMO there and the TPU. What's the minimum sort of thicknesses that you're seeing are usable?
Yeah, it depends on the material, but it's essentially whether it's TPU or nylon PA12. And essentially, we're trying to keep to at least 1.1, 1.2 millimeters in thickness. But it's not just the thickness; it's also how quickly it goes down to that thickness. As
So
well.
radius.
So yes, well, the ramp from a thicker area to a thinner area, we found that really makes a difference. And also whether you're vapor polishing as well, because once you're vapor polishing, then you've got competing priorities as well in regards to that. So the vapor finish tries to go to the thicker areas, the more solid areas. But if you're trying to get some so if you're trying to go have some really rigid parts in the material, you need to ramp it so that the vapor finish can essentially go to these thick areas and the rigid areas as well as the thin areas. So these are all considerations depending on if you have vapor finish or not as well.
Got you. And there's a question about vapor finishing and does it improve the mechanical performance? And the short answer is absolutely, because what you're doing is you're eliminating a stress riser. And like Corey said, you want to avoid that crack initiation. And by flowing the surface of the part and making it smooth, you're eliminating those stress risers. You can't do that mechanically with blasting or mechanical polishing because you're just smoothing the surface over. You're not actually like eliminating the stress risers between the particles on the surface. So thanks for that, Corey. So we've got another question here, maybe just throw to you, Simon, which is around TGA approval for Australia for materials. Do you want to give us a quick sort of summary on that?
I'd love to, Joe, but I think our session is literally just about to end. I think it might be something which we might have to bring up at another stage. But I mean, look, the short answer is, look, the TGA is, this industry is something which the TGA is starting to look at quite closely. I know Corey's team is already on the front foot in terms of developing, having the process rigor, but also the material qualification rigor as well. So the short answer is yes, we can. All of the materials which HP run and a lot of the other technologies as well have been certified for skin contact. So yeah, all of those data sheets are available to us and happy to sort of pass those on.
Just one more question here, and unfortunately the others will have to take offline, but maybe throw to you, Aileen. Someone's asking about build density and printing sockets in a build. Quite expensive because they're large parts with a large volume. What are you seeing people are doing overseas with how they're packing their builds?
So we have a lot of customers printing prosthetic sockets. We can pack between 7-8 sockets in a build buckets, which is quite affordable when you do that kind of nesting for a prosthetic socket. Also, we are seeing customers that are printing 2 materials for the socket in different buckets. So there are ways to optimize the nesting and ways to optimize the cost.
Right, thank you. Well, apologies if we didn't get to all the questions there, but yeah, thanks for your time. We really appreciate it. Hopefully you got a sense of the passion that we all share, and yeah, we look forward to hearing from you after the session. All the best.
All the best. Thank you very much.
Thanks, everyone.